Hello everyone, my name is Nasser, currently in BTech final year of electronics engineering student from Aligarh Muslim University, Aligarh. So in this video, I'll show you the complete CMOS design flow in Cadence Virtuoso and starting from the schematic design, simulation, layout, DRC, verification, and finally exporting the GDSII. So uh, we'll go to the search bar and we will open the remote desktop connection, connect, yes, and we will enter the username and password, Nasser 22ELP244, and password. Okay, we have given the username and password and then enter. Okay, as you can see here, the Linux CentOS 7 has opened. And now in this, firstly I will create a folder name, like right click, new folder. You can give any folder name, like right now I have made the Schmitt Trigger, so I named it, and the folder name, any assignment, if it is assignment, you can delegate assignment, or like assignment digital IC. I have given the assignment to folder name. Okay, I have already created, so I'm not going to create it again. Okay, moving ahead. So we'll click open in terminal. Okay, enter the command, firstly the csh, enter, and source home cadence csh enter, and virtuoso and enter. Here the log file will open. Okay, maximize it. As you can see here, the log file has opened. And now uh, we'll go to the file, we'll create the library name, any library name you want to give, you can. For example, and I'm giving, and I have given the test, and okay, and you will hear it is to an existing technology library. Existing technology library means that what which technology node you is use, like GPTK 90, whatever the technology node existing in this cadence. Okay, and you will click OK, and after that you will go to file again and new, and you select the whatever the library name you has given, you have to give here, and the new cell you have to give the name, like Schmitt Trigger. Okay, so here I will give the Schmitt Trigger name, but I have already made it, so I'm not going to create it again. Okay, so basically I'm going to make the Schmitt Trigger. So an Schmitt Trigger is a special type of computer circuit that introduces hysteresis. That is, meaning it has two different threshold voltages, one for switching from low to high and another for switching from high to low. So this prevents false triggering due to noise or slowly varying the input signals. Basically, it converts the sine input wave to a digital output wave. So going to file, open, and I have already created the library name and the cell, and the view is schematic, cell is a schematic trigger, test, and click OK. Session, it will open the schematic which I have made already. So here click F for to fit the screen. I have created it. As you can see here, I have created the schematic of the schematic trigger. So from the image, you can see here this schematic looks like the schematic trigger, especially the CMOS schematic trigger. So it has two PMOS transistors, this and this, uh, and two NMOS at the bottom, arranged in a cross-coupled manner. So the input is fed to both NMOS and PMOS gates, while the output is taken from uh, the a middle node connected to an uh, inverter tail. The positive feedback loop between transistor confirms the schematic trigger behavior, so it aids hysteresis to avoid the noise at the switching threshold. Okay, So now, moving ahead, um, and how I have created, created this, how I have taken this nmos 1v pmos 1 pmos 1v pmos 1v nmos 1v nmos 1v. Here you can go to the create instance, add instance, browse. So I have used the 90 nanometer technology. So you can go to the gptk 90. Okay, you can select nmos 1v. If you select nmos 1v, it will appear here. You can see the length, the width, the finger width. Okay, so here it will appear like this, in this way. So, and similarly, you can also select the pmos by clicking here, going to create instance, browse, and you can also click here you can see the pmos 1v is also appearing here. So here the arrow is from upward. So uh, the pmos can also be selected in this way. So I have already made it. So we can cut this and cut this. Okay, keep, press escape to. So this is the schematic of the Schmitt trigger. So now, moving ahead, you can also place the pin that is here, VDD, V in, V out, GND. How to place the pin? Go to the pin placement. Pin placement. You can create here. You can give the name of the pin, V in, VDD, and and V in, VDD, GND is the input, and V out is the output. So direction, you have to also choose the direction. If we are giving the V out, you have to also give the direction is output. Okay. So in this way we can create this schematic, and this is the narrow wire. Here you can see the narrow wire. By the narrow wire we can connect all these connections. Okay, so this is the way of creating the schematic. Now after this, I will create the test bench. That is the test bench is like here you can see. I'm going to show you again. So we can uh, go to the file. Okay, so test bench is basically created from the uh, schematic. Okay, by placing the pin, and here test bench is like here you can see. You can also there should be the same library name, only the cell view should be changed. Test bench is basically the compact form of the schematic. If the suppose if the schematic is very large, we can use the whole schematic in a box, like here you can see the whole box, and here it is VDD, V out, GND, and V. So it is very easily to analyze the simulation result. So we use this test bench, or we have made the symbol. You can also say the symbol. Okay, so in this, this is the schematic. This is schematic trigger circuit, and I have given the VDC, that is the source voltage, and the input voltage in the sine form. So in the input voltage sine form, we have given the amplitude 1.2 volt and frequency 5 kilohertz, and the source voltage have VDC volt of 1.8 volt. Okay, so now moving ahead. Now uh, after this, I will go for the simulation. So for simulation, we will go to the launch, and how to just uh, take this in, like we have given the sine, GND, and VDC. So we can go to the create instance, browse, and this sine wave, V sine, or the VDC, or the ground. We can go to the analog library. From the analog library, we can select if we type V sine here, V sine has appeared, and in the similar way, you can also check for VDC and VDC. You can see here VDC has appeared. You can give here the DC voltage, VDC. Okay, and in the similar way you can also choose the ground. So now going to launch, I'm going to show you the simulation result. There is the transient analysis. Transient analysis is basically the response of the output with respect to the time. Okay, so go to launch, ADEL here. it is taking time. Session. Okay, it just take time. Just wait for a while. Session. Session. Okay, so now here the ADEL when has opened. So now we'll go to the analysis. So here you can see the different types of analysis. Here the transient analysis, DC analysis, AC analysis with respect to frequency, noise, XF, and all there are very different types of analysis you can do. So I'm going to do only the transient analysis here to see the uh, output. So here I will give the stop time 2 millisecond. Okay, moderate, apply. Okay, as you can see here, it is appeared here transient analysis enabled for 2 milliseconds. And now I will plot the output to be plotted. Select on design. Okay, so here design one for the layout. We are going to only show see the output and input, and one for the input. So here it will appear. You can see here the output and input name has been appeared, or the signal has been appeared here. So now I will go to the run, click the run button. You can see here I have clicked the run button. The log file is open. If there is any error, it will appear here. If there is no error, the simulation result will appear. As you can see here, uh, the input and output waveform has appeared. Input, as we have given the sine wave as an input, and we are getting the output as an square wave, which is the main motive of this circuit. Okay, so now we can see here the output. If is this is the output square wave, and the input, this is the input. Okay, so this is one part of the uh, circuit, and one part of the assignment has been completed. So now moving ahead, and we can cut this, and now I will go for the layout, that is from the schematic to the layout. So now moving ahead, we can cut this, or we can also cut this, we can also cut this. Do you want to save the canvas? No. Okay, then also cut this. So till here I have shown you how to make the schematic, how to make the uh, test bench of the schematic, and how to calculate the uh, transient analysis of the circuit. So now after this, I will explain how to make the layout, and how to check the TRC, LVS, and Asura Quantus, and finally then GDS file. So now going to the file. Okay, open the initial circuit. This is the initial circuit. So here, from here I will extract the layout. So now how to extract the layout? uh, this is the circuit. Go to the launch. From here you can see I have already told you how to do the transient analysis by ADL. And if we want to extract the layout, go to the layout x out XL. Okay, okay, you can give the here the name layout X, and whatever. Suppose I'm giving you the name. I've already made, but I'm showing you how to make it. And LY OUT. Okay, so here if you click OK, it will appear session. As you can see here, the layout, this is the window of the layout. Okay, this is the window of the layout, and from here, and you can and create connectivity. From the connectivity you can generate it all from sources, And if you will click all from sources, suppose you have to generate give the spacing bit is of 0.12, and input output pins, here you will have to change from poly to metal 1. It will appear here as I have given the 0.12 spacing, and then apply. If you apply here uh, the all the NMOS PMOS will appear here. Now I'm showing you how I have done it already. I'm going to show you again. Okay, go to file, open. I've already made. I'm showing you now layout 1. So here you can see the library name test cell is Schmitt Trigger layer 1, and view is of layout. As now I'm going to show you the layout. So click OK. It will open. As we can see here, the exact transformation from schematic to the layout. These are the I'm expanding it. You can see here these are the PMOS, 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 and similarly NMOS, NMOS, and here NMOS. Okay, and these are all the connections. So let it open. Click F for the fit screen. Okay, so now here you can see. First of all, I'll detach it. How to detach it? Go to the options, display. Here, stop time should be 10, and click OK. Here the body has been detached. Okay, there is also another way to detach, and I have already made, so it is a very easy way to detach it. Otherwise you have to select it and you have to click right, uh, or you can also click O by the only the by the options. Here the by option, so by the options you have to detach it. Okay, so in this there are horizontal rail and the vertical rail. These are the horizontal rail, which is, sorry, both this both the horizontal rail is connected, one to VDD and one horizontal rail is connected to ground. And this blue layer is of metal 1 line, and this green layer is of metal, sorry, it is a green layer of poly, and this the red layer layout is of a metal 2 line. Okay, and uh, this a small box is uh, poly. Basically it is used for connecting the two different wires. For example, if we want to connect the metal to the poly, then we will use the this via, this is called the via. Okay, so click F, because if we want to cross from one metal to another metal, or from the same metal, then we directly do not, we can't cross from one metal to different metal. For example, here the one metal one line cannot cross this metal one line, otherwise it will short the circuit, and it will short the layout, which will be error, which will give the error in the DRC. Okay, similarly, however, poly can be can cross to another poly. Okay, and this is also via, which is connected to metal 2 and metal 1. So here we can see this is the complete layout of that schematic, which I have shown you already. So now moving ahead, and now I will check the DRC rule. DRC, that is the design check rule basic. So now going for the DRC check, going to Asura. Here here if my technology file is not added, then you have to add the technology file by uh, clicking on these three dots. You will go to home, then Cadence, then Foundry, then Analog, then 90 nanometer, then Asura Tech Live. Okay, I have already done it, so it is already shown here. Okay, pause. Click on Asura, run DRC, run on DRC. Okay, here you can see run DRC, layout design source, and library name should be test. Cell is my schematic trigger 11, and it is of the view layout. Okay, and the technology file must be added, otherwise it will show you the error. Here I have added the GPTK 90 already. So click OK, OK, and OK. You can see here. Yes, do you want to see the result of this run? Yes. As you can see here, there is no DRC error found. It means that uh, if your DRC, that is design rule check, shows no errors, it means your layout follows all the fabrication design rules defined by the process, that is GPTK 90. Okay. When you run DRC in Cadence Virtuoso layout, the tool checks if your layout violates any physical spacing, width, overlapping, or enclosure rules. So, if it says DRC is completed, that if it is DRC completed, that is zero is found, it means all poly, metal, diffusion, contact, and via layer meet the minimum design rules. There are no shorts or spacing violations, and your layout is manufacturable according to the foundry's rule. Okay. So now we will go to, okay, we can now close this, and now we will go to the LVS. LVS is basically the design versus layout. So again we will go to sudo run LVS. Here we can see uh, the library name should be test, cell is Schmitt Trigger, and view should be a schematic. Here most of the student done mistake, the view they left as a layout. So we will remove this and we'll write a schematic, and in the second layout design source there is a schematic design source, and this should be the layout design source. Layout design source, the library test, cell is a Schmitt Trigger, and view should be layout. The technology file should be GDSII. Okay, we will apply and okay. Okay, click on OK. It will take some time. Here there is some maybe warning is given here little bit. Initially I have done, there was no any warning, but here don't know why there is a mistake given. However, I have done it already, no problem, we can move ahead. Okay, and this is the way of LVS, and in a similar way we can also check the uh, Quantus. In Quantus, run Asura Quantus. It is basically done for the RC extraction. You can see here Quantus parasitic extraction. RC, that is RC extraction. How is capacitor or resistor is connected. You can see technology nodes will be GPTK 90, and spice output should be not spice, it should be extracted view. Okay, and you can see here, you can see, oh, sorry, it should be extracted view. Okay, here you can see pre-resistor, pre-capacitor, uh, pin inductor. Okay, and if you click OK, you will get the RC extraction uh, of this layout. So in this way uh, we can see, I have told you how to make the schematic, then layout, then how to check the DRC, then how to check the LVS, and then how to check the uh, Asura Quantus, that is for the RC extraction. Now we will move to the next part of this video, that is the pre-layout and post-layout simulation, which I'm going to do right now. Now I'll cut this. Okay, so basically post-layout or pre-layout simulation is basically uh, the delay difference. Okay, the delay difference between the initial, that is the before layout, and the delay the after the layout. So I'm going to the file, open. So go to Schematic Trigger, and here you have to make the configuration file by same procedure, by going to file, then you have to use some template there. For example, I'm going to show you the example. Cut this into file, new library, sorry, file, new, cell view. Here you can see here there are different test is everything is same, and you have to change the cell view, and you can see here the configuration file should be there. Okay, and there should be the cell name, and if you click OK, if you click OK, and here the cell name should be like inverter TV. Okay, click OK, already exist. And you can also name some like TB1. You can see here uh, the library, the cell, Schmitt Trigger, view. First of all, use template, and there should be spectre like. Okay, now my view should be changed. Library name is test cell, and this 1 second. Okay, and here I have not the view should be changed. The cell is false cells here, and now I'm just going to show you the real one which I have made. Okay, cut this, go to file, open, and this will be test. View is configuration, click OK. Here you can see, okay, this one. So this is the pre-layout simulation I'm going to show you. So going to the launch ADEL, there is the analog design environment, open. It will take time. Okay, so team transient analysis, stop time is same which I have done already earlier. Click OK, and outputs to be plotted. Select on design, the one out here, and the input is here. You can see here the input and output has been saved. Now click on OK, run button. Here the input and output has been shown as we have already done it. This now we'll go to tools, we'll calculate delay calculator. Okay, and in this here we got a special function that is and delay calculation we are doing here. Okay, we'll remove this, also remove this, and also remove this. So go to signal 1. Here signal 1, suppose input I am taking, select this. Yes, signal 1 has appeared. Now signal 2, click on signal 2, click on signal 2, that is this. Here you can see the signal 1 and signal 2 has been appeared. Now the threshold voltage is 0.9, which is half of the 1.8, and now click on everything is fine. Now click on OK. You can see here the formula has been appeared, delay calculation. So click on you can see here the delay is of 5.9 microsecond, and this is the pre-layout simulation. The similar can be done with the post layout simulation. Example, we can cut this now, we can also cut this now, we can also cut this, don't want to save. Okay, okay, so that was the pre-layout simulation. Then for the post layout simulation you can go to tree, and here set instance view. You will see the if you have done the RC extraction, you can see the extracted view, and for that and after that you will calculate the post layout simulation. Okay, now I'm not going to do that, and now I'm going to calculate the I'm going to create the GDSII file. For the GDSII file there is some rule. I will go to file, export, go to the stream, in extreme, and you will name the give the test, and you will give the GDS file, save. Do you want to replace it? I have already done because it is given option. Yes, you can see, and you can give the library name. The library name is here. The library name is test, and the layout Schmitt Trigger. Okay, okay, and the technology file should be of uh, where it is 90 GPD 90. Okay, and you can extend it further. You use automatic layout mapping, and now translate a non-zero site file with same exit. Do you want to? Okay, there is zero error and some warnings. Just ignore that warning. You want to see the log file? Yes, you can see here the log file. If there is any error or warning is occurring, then it will show here. Okay, so now moving ahead. Now I have export the file. Now I will import that in the same stream file. Okay, we'll give the location, and it should be test, and file name is, I think, Schmitt Trigger.